this lecture finishes chapter 1. So hang on, we've got a few slides to go to. Now we're going to talk about radio frequency signals and signal strength and some of the tools that are used to measure them. So we're going to try to understand how to detect an RF signal, what kind of factors, the type of Wi-Fi scanning tools, what a client signal strength reports, comparison between, some of your systems show you the RSSI, or the received signal strength indication, and dBm versus that. And then we'll look at output power versus received signal strength. So those are kind of the objectives we're going to try to hopefully get through in this section. So let's talk about the behaviors in RF signal, and it's basically with the signal strength. Now, signal strength, remember, is just the amplitude of the received signal. It's not the output power of the transmitter. It's what is received. Now, there's a term called noise floor, which basically is the general RF noise in the environment. You may also hear it called ambient noise. With all the electronics, computers, motors running around, it generates a certain amount of noise that is background noise, and to have any valid RF signal to be received, you've got to be above that noise floor. Now, the term interference is intermittent RF energy that at certain amplitudes can impact the ability of a receiver to hear something. Those are the three major categories, behaviors that when you're planning a system, you need to take into consideration. Now, if you look at the comparison between, you've probably heard this thing, signal to noise floor ratio. It's a metric that says how much above the signal, how much above the noise floor am I? And when you talk about a signal to floor ratio, or you may hear it called SNR, but that signal to noise, the larger the number, it basically means I can put more modulation types, I can achieve higher data rates. We'll get more into that later, but just know that when I see a signal to noise ratio that's larger, that means I've got a higher probability of getting better, faster signals through it. Now, in the other case is signal to noise, signal to interference ratio, and that's an SINR, signal to interference noise ratio. And it's it's the signal strength, noise floor, and interference that if a generator kicks in and sends a burst of RF energy, you've got to make sure that you're above your interference level. So you want to make sure that when you're considering signal to noise or signal to interference ratio, you want to make sure that there's as much difference between those as possible. That way, at least, when you have that much clearance between signal to noise and above your interference, it allows you higher data rates and just better signal. Now, signal strength is measured in a lot of different ways. Sometimes you hear the term watt, and watt is basically the output power at the transmitter. Now, that's what you got to remember. It's at the transmitter. It's not to be confused, not to be used to measure what's received, but it's just what is being transmitted, what power is being transmitted out of the transmitter. Now, milliwatt, because a lot of the devices, transmitters we use in wireless networks use very low power. Milliwatt is 1/1000th of a watt, and you'll hear it, you'll see it, like here you see it abbreviated MW, capital W, milliwatt. The next term you're going to see is dB, decibel, and basically decibel is just a comparative or relative measure between two power levels. So it's just one way of comparing this. Now, when you see dBm, that actually is decibel measured, so it's an actual measurement of difference, and the M stands for milliwatt. So it kind of says, well, how many decibels is it relative to like 1 milliwatt? So when you got 0 dBm equals 1 milliwatt. And since receivers in a lot of wireless devices are very, very sensitive, it's just a whole lot easier to refer to them in dBm than it is to do it in milliwatt. And then the last term you're going to hear is received signal strength indicator, the RSSI. Now the I-802.11 standard put in a variable or an arbitrary metric to try to measure received signal strength, but there's no actual rule on how to set it up. So each vendor has kind of picked and choose what it wants to do. So if your vendor uses RSSI, definitely check the owner's manual to see how is it being measured. Now, some of the newer stuff is kind of falling away, and most of it's all in dBm. So just know that you may see that term out there, but it's just kind of falling out of the wayside. Now, the question is, how do I scan this stuff? How do I how do I know what's out there? The wireless LAN has plenty of different scanners, some free, some expensive, some professional grade. Your computer, if you're using a Windows computer, has a scanner if it's got a wireless antenna. If it's your desktop, you may not have a wireless, but your laptop and stuff like that does have a command called net shell. And it basically shows what it is. Though the command you're looking at there says it's net shell wireless LAN, show the networks in mode of the base station, BSSID command, and it then displays all the networks out there and their signals and their rates that are being used. In preparing for the test, you may want to look at net shell and see what other options and other commands that may be beneficial to you. As we go through this, I'll probably give you different commands that you want to keep in mind before we get far enough down the road. Now, there are definitely, your PC version, it gives you the data, but some of us like more graphical use and pictures, and a picture says 1,000 words. So you see a lot of graphical tools. The one here is analytic, Wi-Fi, and it gives you specific, very detailed pictures. So when you highlight one, when you see that it highlighted this one in green, and then it gives you different results, and it says, hey, what at different points in time of data, what the signal strength is, if it's good, bad, strong, weak. It gives you an indicator as to what channel you're on, what 802.11 is, what its max speed, what kind of security is on it. So it gives a lot of information to help you analyze what that, how to know what's in the area that when you're designing a system. Yeah, there we go. Here's just an advanced school. Here's one in, sensing tracking a signal over time. So this one's on a Mac OS. It's called Wi-Fi Explorer. But it's similar in nature. It gives a lot of specific detail, the signal, the channel, what its bandwidth is, what band it's in, what's its max data rate. And then this one does the signal over time. So you can kind of tell what's happening. So there are definitely a lot of tools out there, and we'll probably play with a few as the semester goes on. I'll probably have you do some lab work and try to assess what kind of environment you're in as you're analyzing this. Now that you understand a little bit about basic RF stuff, whoops, pushed the wrong thing. That the question is, how does Wi-Fi use this to transmit and receive data? And basically, you get two different things are involved: modulation and coding. Now, modulation is a way to get bits onto an RF medium. So because the RF wave is what's being used to carry the data, and when you do that, it's called a carrier wave. But when that wave has been modulated, it's now called a signal. So if it's just sending out there an RF wave used to carry data, just call it a carrier wave. But once you modulate it, once you try to put information on that wave, it's now called a signal. So when you hear the term signal, you want to make sure you reference it to as a modulated RF wave, at least in the context that we're in this class. Now, coding is used to getting bits of ready for modulation. So it's kind of like I'm taking the data and I'm going to manipulate it in such a way that I can put it on the carrier wave. So coding is a way to encode data before it's modulated onto a carrier wave, making it then a signal. Now, coding provides a method for some level of recoverability. So if you know what cover it is, if some error comes in, you can sometimes recover the data if it gets transmitted in error or it receives some interference. But if it's unable to recover what that message is, you'll have to have it resend again. You'll have to retransmit. Now, when you put modulation and coding together, in result, you get a data rate that is achieved. And as you can see here, based on different modulation techniques, different coding schemes, you're seeing that the data rates change. They increase. So based on the modulation, based on the coding rate, you start seeing the data rate changes. So just know that those two, the different modulation techniques and the coding is probably beyond the scope of this class, but just know that between coding and modulation, those two together is what gives us that data rate. Let's see, anything else I need to say about this chart here? Gives you modulation. 802.11 provides a way to represent different modulation schemes and coding schemes, MCS. So just know that there's several out there. And just know that coding and modulation are the two keys to increase your data rate. So as you're seeing us move towards wireless gigabit, know that the coding and modulation techniques have changed in such a way to put that much data on your carrier wave to create that signal. So this chapter, we covered a lot of information. You found out what a wavelength was, what higher and lower frequencies, what amplitude is, that it's the power of the wave, phase being a comparative between relative attributes that relates one wave to another. Modulation uses phase shift keying and amplitude shift keying in wireless LANs. We don't use frequency shift keying, so phase and amplitude shift are used. Let's see, RF waves are reflected. Okay. They're refracted as they pass through some things. It may bend. Now you understand reflected, it's like a mirror, right? Okay. Diffraction says it encounters an object that is larger than in relationship to its wavelength. It'll bend. You've got, what about scattering? Scattering is if I hit an uneven surface and I get a lot of several different reflections. Absorption, that knowing that as RF penetrates, some materials, it gets absorbed and turned into to heat, basically. So as the RF energy is going through a device, it can't, at an atomic level, it can't absorb everything. It can't pass it through the same sequence. So then it proceeds to turn into heat, which then diminishes the strength coming on the outside. Now, absorption results also deal with attenuation, where the signal is degrading over space and time. So when you look at where your access point is at home, when you're sitting on the living room couch, the question is, okay, where's the access point and how many walls, doors, furniture, plants is it going through before it gets to your receiver on your laptop? And that shows you that, hey, it's degrading a long time. It's being absorbed. It's being, a lot of these things, it's being absorbed, it's being reflected, it's being changed to get, by the time it gets to you, it may be weaker than you anticipate. Now, keep in mind that RF transmission power is also referenced in watts. That's transmission, but in most of our, Wi-Fi, wireless LAN discussions, it'll be discussed in milliwatt. But the received signal strength is done in dBm, even though you still see some manufacturers doing RSSI. But most of your better ones, and probably most of what we're going to talk about in this class, will be all in dBm. 802.11 devices uses a code modulation encoding scheme, MCS, to achieve the data rate. It's just, you don't need to know the details of how they're all calculated, just know that those exist. And in addition to modulation encoding, the system also uses channel width and spatial streams that increase the data rate. And we'll get a whole lot more into those a little bit later, but just know that that's how, when you're looking at 802.11n or 802.11ac, you're using different channel rates. You're doing, you've got multiple MIMO that we talked about last session, and how many different spatial streams, how many streams am I sending? All of that stuff has an impact in the achievable data rate. So I hope that gives you a summary of what went on in Chapter 1. It's a long chapter. We covered it in 3 different sections. If you have any questions, let me know. Have a great day. Bye-bye.